Okay, we're going to continue on here. We got into really the kind of main topic of this class, which is equilibrium or chemical equilibrium. And as we sort of touched upon at the end last time, we kind of got into this chapter. Chemical equilibrium does involve a specific type of reaction, and it is a reversible reaction where you do see, again, both of these arrows. And that implies that this reaction does head in both directions. And the two directions that they are commonly referred to is if you're heading from reactants towards the product side, that is what is referred to as the forward direction of this reaction. And what will happen in these type of reactions is at some point you will build up enough products that the products will then come back together and recombine, and we'll start heading in the opposite direction from products back to reactants. And that is what is referred to as the reverse direction. So you can think of these reactions really as a two-way street where it is heading in both directions. Eventually, it will reach chemical equilibrium. And as we talked about last time, and we'll probably talk about more as we go through this chapter, a reminder that people oftentimes have a wrong idea about when we talk about chemical equilibrium of what it represents. It does not represent necessarily that you have equal amounts of everything. It's really talking about what we were talking about in the previous chapter, which is the kinetics of the reaction, the rates of the reaction. So when something reaches chemical equilibrium, it is that rate of that forward direction will eventually equal the rate of the reverse direction. And as we touched upon last time, what essentially will happen at that point is because just as quick as you kind of make products, those guys are just going to send back the other way. They're just kind of equally going back and forth. It will essentially lock everybody into place in terms of their concentrations. If you're thinking about their concentrations, if you're dealing with gases, it will also lock in their pressures because their concentrations aren't changing as well. So everything gets locked into place. And they will be able to, again, maintain that as long as you don't kind of do anything to screw up the equilibrium. Um, but they will basically just maintain their concentrations, whatever they may be. And again, they may not be equal on both sides, but they will be able to sort of maintain those concentrations. Now, one of the things that we also talked about a little bit, and again, we'll see more in this chapter, is you can do something to this reaction that would mess up the equilibrium and the rate of the forward and reverse reaction. And these reactions are sort of, if you want to think about it, self-correcting. So even if you do something to it that kind of screws it up, it will by itself try to adjust itself back to that equilibrium state. So its ultimate goal, if you want to think about it that way, is to kind of always reach sort of that equilibrium state or get itself back to the equilibrium state if something happens to it. Now, one of the things that we talked about, and we'll continue here on, but first off, any questions on that? Okay, so continuing on and kind of touch on some other things that we sort of talked about as well last time. Um, the equilibrium state is really a lot of activity that's happening, even though, as I mentioned last time, you may do a reaction and your reaction may just turn red. And again, your test tube may remain red the whole entire time. And it may look like to you on sort of the big level there, the macroscopic level, that nothing is happening. But again, on the molecular level, there's a lot of activity that's happening to maintain, for example, like that red color that you actually see in like the flask and stuff like that. There's a lot of reactants going to products. There's a lot of products going to reactants, again, at the same rate, locking everybody into place, which is why if it's something sort of color dependent, this is why the red gets locked into your flask and stays red, because, everybody's locked at that concentration where we have the right appropriation to make sort of a red solution, for example, as an example of a color. And so there is always a lot of activity, even though, like I said, it sort of looks like and there's not much going on. It's all over at this point, but there is a lot of activity still going on to maintain that. So that's why I said again, macroscopically, it is static, but microscopically, there's a lot of activity happening. It's very dynamic, and you got a forward reaction and ending reaction happening. Now, if we take a look at a reaction such as N2 plus a little H2 goes to NH3, I'll balance it like I'm in chemistry class or something like that. And in this particular case, we can see here, if this is time zero, basically, um, the only things present at this point are reactants. So in this case, we only have, as you can see from the graph here, our reactants present. We really have none of our products at this point. And this also tells you sort of what you should expect in this case. Because there are only reactants present, the only people that are going to come in contact with each other are reactants. And as they start to collide, the only sort of way this reaction can proceed at this point is in the forward direction, right? Because you have no products to come back the other way at this point. So the only thing that could happen is the forward reaction will occur. And obviously, if the forward reaction will occur, we will start to see some product formation, which is why we start to see our product line here starting to increase. As you hopefully know, right, the only way you can make products is you have to use up some reactants to make the products, right? They have to come together and be used to make those products. And that's also why we see a decrease here in our reactants as it's starting to decrease with time, as those products are starting to make. You will also start to see at some point, maybe we're not decreasing at such a steep rate of our reactants. And maybe here we're not really increasing at a steep rate here of our product formation. And that's probably where we're starting to build up enough products that the reverse reaction is going to start to kick off at this point. So it's not all like a one-way street at this point. We're starting to get enough products here. As we sort of come up this hill, you can see that our products are leveling off, and also this steep decline of our reactants are also leveling off. That would indicate that we're probably getting some reverse reaction heading back to the other way. And at some point, what will eventually happen is we will reach this point where if we look at how the concentration of everybody in this reaction is currently changing, they are all leveled out at this point, right? They have all flatlined. And when the line goes straight, that means that their concentration in this case is not changing, right? So they're kind of locked into place. So that point where you see on this graph that everybody's concentration basically levels out, that is the point where equilibrium has been reached in this reaction. That is the point where, again, our rate of our forward reaction will equal the rate of the reverse reaction in this case. And again, and that's also why, as I mentioned before, at some point it's like all forward to start with, but eventually you'll start to build some products. You'll get some reverse reaction happening. And again, eventually we'll get to the point where both of those guys' rates are going to equal each other. And as I mentioned before, you can see here just from this example, the reactants, the products, they're not all the same concentration, but what is happens when it reaches equilibrium is they all get locked into place where they're at that point when equilibrium is reached. And you can see they're able to really maintain those concentrations sort of indefinitely, as long as you don't kind of do anything to screw it up. They will be able to maintain those concentrations along the way. Any questions all out there? So, as I mentioned before, if we take a look at another example here, we got some water, a little CO, making some H2 and CO2. So initially here, if we are only starting with reactants, the only thing that can happen is you would expect that forward direction to occur. And at some point, like I said, in these reactions, you will build up enough products that we will start to get that reverse reaction to kick into place. And again, we'll eventually hit that point where each of those rates, the forward and reverse, will equal each other and come to equilibrium. So in these type of reactions, as we talked about before, and some things to think about when we get into calculations, is that sort of idea here. If you only have reactants, the only way that thing could head is towards the products, right? Because you have no products to begin with. Remember, as we touched upon as well last time, you could have this reaction where maybe you're starting with all products and you have no reactant. In that case, the only option for that would be it's got to go in the reverse direction because it has no reactants, it's only products. So that reaction has to be heading in that direction. So these are things you want to kind of think about, especially when we get some calculations as to sort of which way the reaction is heading. I would say in a lot of cases, probably 99% of the cases or more, you could probably safely assume it's going to be heading to the reactant side to begin with. But there are situations where it may be actually heading in the opposite direction to begin with as well. We'll talk about those as we go through it. So again, just graphically, when you look at that forward rate and that reverse rate, when they level out and are equal to each other, that again is when chemical equilibrium has been reached. So let's take a look at this sort of example here. If we have this system that's at equilibrium right now in a closed container, and we decided that we wanted to add some more water to the system. Take a moment here and decide what will happen to this equilibrium. Actually, what will happen to the concentrations of everybody if I decide to add more water. So what you want to decide is, will everybody's concentration go up? Will their concentration go down? Or will it stay the same? So take a moment, and if you have this all in a closed container, it is already set up as equilibrium, arrows and all in the beaker container, right? And what would happen if you added some additional H2O? So take a moment, think of what will happen to concentrations of everybody here. Okay, let's take a look. So first off, I'm going to add some water to this, right? Pop the lid open, drop some in, maybe, however we're going to do that. So water's over here, right? So when I do that, should this kick off the forward direction? Should it kick off the reverse direction of this reaction? Should it not make a difference? What do you think? What do you need to come together for a reaction to take place? You need everybody to find each other, right? So if I add more water to this case, right, I am increasing the amount of reactants that I have in this situation, right? So I now have kind of more reactants than I do products. There is probably a better chance at this point that the reactants are going to come across each other faster than, say, our products are going to come across each other just by the availability of it, right? So we talked about factors that affect the rate of reaction in the previous chapter, right? Availability of reactants, right? Concentration of reactants and so forth. So when you dump this water into this situation, you're increasing the amount of reactants that are present. And just by the idea that they're going to find each other quicker, that is most likely going to kick off the forward direction, right? Because now we're going to get reactants, sadly, reacting with each other. And that's going to start our product formation to occur and going to kick off the forward direction in this case. Any questions on that there? Because that happens, what would happen to the concentration of CO? Would I expect it to go up, go down, or stay the same? What do you think? You got like a 33 and a third chance there. Not bad odds. Only be wrong twice, because then you hopefully you get the right answer after that. So I can. What do you think? Should it go up, go down, stay same? Okay. So in order to make products, what do you have to use to make products? Right. So if you're using the reactants, should the concentration go up or down? Go down. Yeah. So you have to use reactants to make products. So we would expect, as the water in this case and the CO start to combine, they are going away, right? Because they're breaking their bonds or reassembling and making products on the other side, right? With that being said, the concentration of H2 should then go up, down, say the same, up, right? Concentration of CO2 should go up as well, right? And again, this is the idea. We basically kicked off the Ford reaction, which essentially is a nice way of saying we're going to make some more products, basically, right? So we should start to see our products increasing. The only way you can make products is you have to use those reactant parts, right? To build those products. So you've got to see the concentration of our reactants go down. What would happen with the water? Up, down, stay the same? Yeah. Overall, what will happen with the water is it should go down. But you artificially added the water, so you would actually see the water jump up high only because you put it in there, right? So you jumped it up. But once it starts reacting with the CO, you then should start to see it come back down. It may actually end up being more than what you started with, only because you artificially added a bunch in there. But overall, once that forward reaction starts kicking off, you'll start to see it also come back down. And again, it may end up a little bit higher just because you added more. But if you followed the trend there, it would peak because you added, and then as it starts reacting with the other reactant, it will start coming down with it. And again, you should start to see a decrease in it overall, basically. Any questions on that? Yeah. No, it's actually a reactant, right? So it's part of the reaction itself. So again, it'd be simply just adding more reactants basically to the system. Other questions? All right, so let's take the same reaction, and what will happen in this case to everybody's concentration? Will it go up? Will it go down? Will it have no change? If in this case we added some H2 instead of water. So take a moment there and decide what will happen to everybody in this situation. Equilibrium. So H2 is over here. Again, should this kick off the forward direction, reverse direction, or no change? Yeah, so again, for the same sort of explanation as what we had in the previous one, in this case, though, we're now adding more products, right? So now the availability of our products is going to be more than our reactants, and that's going to allow them to come together a lot more efficiently. And that should kick off, again, the reverse direction in this case. Again, what that should mean in terms of our CO2, up, down, no change, should go down, right? Because really in the reverse direction here, our products are like our reactants, right? And our reactants are like our products in this case. And we again should see the formation of CO, and its concentration should go up as we start to hit that reverse direction. We also should see the water's concentration increase. And again, with the H2, we'll see a very similar thing to what we would see in the previous example. We will see a spike in it because, again, we added it. But as it starts to react with the CO2 in this reverse direction, we will start to see it come back down. And again, like I said before, you may actually end up a little bit higher than you started with, only because you kind of spike the concentration by adding it. But overall, what's happening is once it starts reacting with the CO2 in that reverse direction, its concentration should also come down. Any questions on that there? So when you do things to equilibrium reactions, one of the things you really want to kind of think about is what I'm doing maybe kicking off like the forward direction of that reaction? Is it kicking off like the reverse direction? Is it maybe not doing anything? That is an option. We'll talk about that later on in the chapter. But ultimately, if you have a system that has equilibrium and you do something to it, what you want to kind of just try to think about is, what did I just do? Did I have that forward happen reaction, reverse reaction happening? And that'll give you a lot of information about what's happening with everybody in that reaction. Are they increasing? Are they decreasing? And things like that. So those are things you want to kind of keep in mind as you go through this chapter. That's the one we saw earlier, so we don't look at it again. So let's talk a little bit about the equilibrium constant and its application. So here we go. If we got this reaction right here, N2O4 goes to 2NO2, there is a relationship known as capital K here. And again, as we saw in the previous chapter, lowercase k is the rate constant. Capital K is the equilibrium constant. Keep that in mind when you're writing your lab report for the rate experiments there. That's a lowercase k because by this time, when everybody goes to write their lab reports, we're deep into capital K. So all the K's on their lab reports are all capital K. So lowercase k for rate constant. This is the equilibrium constant. And in this case, basically the equilibrium constant is the concentration of your products divided by the concentration of your reactants. So it is basically this ratio of products to reactants. Now, in this particular case, the number is not super important for us at this point, but for this particular reaction, but you can see how we get it. And we actually do take the coefficients into account when we do this relationship. So the products here is our NO2, its coefficient is 2. So we do have to take the concentration of NO2 and we do need to square it because of the coefficient. By the way, once again, the little brackets do mean concentration, and typically it is molarity that we're talking about when we do that, which is again our obviously moles per liter. And over here, the coefficient is 1, so that is why we don't do anything with it over here. It's basically to the first power here. In general, if you have a reaction, you take your products over your reactants. Once again, we do use our coefficients as the exponents here when we do that. And when you do this with concentrations, this is sometimes referred to as the Kc value. I'm going to go with concentration for C there on the bottom. Seems logical to me. This is our first K, perhaps of many to come. Yes. Again, this class is brought to you by the letter K. Yes. We're going to need to see every K that you, again, probably don't want to see. So what is this? This is the ratio of products to reactants, the concentration of it. What does equilibrium constant tell us? First off, a couple of things that we maybe touched upon as we got into our conversation last time. The equilibrium constant is a constant value for a particular reaction, and it is a constant value as long as, again, you keep the temperature the same. So as the temperature remains the same and you do this reaction, and as we talked about, it doesn't matter if you start with all reactants, all products, a little bit of everybody, that ratio of products to reactants will always be the same number as long as that temperature is the same for all those, experiments that maybe you did. So what does it tell us? Well, if I have a K value that is large, what do you think that would mean? When I reach equilibrium, would I mainly expect to have reactants, products, or like the same above? I would expect to have more products. Just mathematically speaking, if you take a large number divided by a small number, you end up with a large number. So one of the things the equilibrium constant tells you is if you have a large value for it, it means that when you reach equilibrium, you would mainly expect to see products present. Yeah. Vice versa, if you have a small value of K, you would expect to have more reactants present. And it's the same math. If you take a small number on top divided by a larger number on the bottom, that's going to give you a smaller number. There is incredibly different degrees of sort of large and small values of K. There are large values of K that are like times 10 to the 54. There are small values of K like, times 10 to the minus 36. And anywhere in between. So what is really considered a large value of K versus a small value of K? It is that large number of 1. Yes. So anything that is 1 and above is considered a large value of K. Anything that is less than 1 is considered a small value of K. And like I said, there's definitely extremes and anywhere in between those numbers, but 1 is considered a large value of K, and anything above it is considered large. Anything less is considered small. Now, a nice thing about K is it is just a number. There are no units associated with K. So it is just simply a number that gives you some important information about what's happening in this reaction. So K is, again, just a number. And as I talked about the other day, you can do these reactions with, like I said, all reactants, all products, a little bit of everybody. And this is sometimes a very hard concept for people, as I was maybe talking about last time, that, people think, well, even if I did all reactants, but I use different amounts of reactants, when it reaches equilibrium, I feel like I should have a different sort of number there because, again, I didn't use the exact same amount in each of those experiments. But remember, what we're looking at here is that ratio of products to reactants is going to yield you a constant value. And as I might have did the other day, because the equilibrium constant is, again, products over reactants, just say, again, we wanted our equilibrium constant is going to be 2, for example, right? As I said before, just thinking about it mathematically, there's many different sort of ratios that will end you up at 2, right? I could have, again, 2 divided by 1 is 2. I could have 4 divided by 2 is 2. I could have 16 divided by 8, get some big math here, divided by that will give you 2. So although these are all obviously different numbers, the ratio of all those guys end up being the same in terms of the proportion of products to reactants. And that's why in these equilibrium reactions, again, you can start at many different spots and you always end up with that same ratio, not necessarily the same numbers every single time for everybody, but when you take the ratio of your products to reactants, you will end up with that same equilibrium constant value along the way. Any questions out there? Now, we'll turn the page here. Take a look at that, I think. So as I just mentioned, looking at the value of the equilibrium constant again gives you that really important piece of information of sort of where the equilibrium lies. And, just because, again, you do have or would expect more products or reactants, depending on the value of the equilibrium constant, it doesn't mean that you don't have anything on the other side. Yeah. Even in the extreme cases where you have a giant equilibrium constant, like times 10 to the 54 type number, even though essentially with an equilibrium constant like super large like that, it is essentially a one-way street heading to the products. There will always be a little bit of it kind of cranking itself back in the other direction. So you will always have a little bit of everybody kind of in there when it reaches equilibrium, even though it's maybe lopsided one way versus the other. But there is always a reversible sort of situation that's occurring, even at those really extreme sort of situations. We will see an equilibrium constant, for example, for things, as you may remember from Chem 50, solubility rules, right? And there are certain things that when you look at those rules, they say that thing is insoluble. It should be a solid in solution. Even something like that, that should technically be a solid in solution, is considered insoluble. A little bit of it will still be broken apart into ions, even though it's almost 100% or 99% all solid. It is a reversible sort of reaction that's happening, and you will still have a little bit of those kind of free floating ions in there that didn't precipitate out. And there's always that little bit that's always going to be there, even at the extremes. And we could also use these things to help us do things, and we'll actually do this in an upcoming experiment, is we can actually, if we want a reaction to kind of just go one direction versus the other, we could really force it to do so by adding a lot more, say, reactants. So if we wanted the reaction to kind of almost go completely to the right, we could kind of have a really high concentration of a reactant, and that availability of those reactants is just going to force the reaction in that forward direction to occur. And we could kind of push it one way or the other and kind of manipulate it really well. All right, so here when we look at this reaction of Mickey starting his day here, and then after a long day, Mickey's upside down there. The equilibrium constant is 25. When this reaches equilibrium, should we expect mainly reactants or products in this case? We should expect, again, mainly products, as essentially it is products, right, over reactants. And again, 25 is considered a large value of K, anything again above 1 there, 1 and above. And that would mean that we would expect the reaction probably to head in this direction. And we probably should have some pretty good concentrations happening on that side of our products. Once again, still means we have some reactants there at this point, but we would mainly see products at this point. So we could write this equilibrium constant as I just did there. And again, as I mentioned before, sometimes referred to as a Kc value as it deals with concentrations. But if we have a homogeneous equilibrium, just like homogeneous mixture, which means everybody's the same, what we're talking about here is the state of everybody in this reaction is the same. Everybody here is gases, right? And one of the other sort of fundamental properties that we associate with gases is pressure, right? So a lot of times we don't really look at concentration a lot with gases, but we do follow pressure. So in addition to an equilibrium constant there, the Kc that deals with concentrations, because we do have gases here, we could also write an equilibrium concentration that deals with equilibrium concentration, our equilibrium constant that deals with pressures. And it works the same way. It is still products over reactants, except that this is the partial pressure, again, squared because of the coefficient of our product there, NO2, divided by the partial pressure of our reactant, which again is a 1. And again, that's why there's nothing there in this particular case. And surprisingly enough, maybe not, adding to our very quickly growing list of K values, this is known as a Kp value. P, I'm going with pressure on this situation on this one. So Kc usually deals with concentrations. To be honest with you, typically that should probably be molarity if you're doing calculations with it. Kp, I would say in general, when you're doing equilibrium sort of calculations, and especially later on when we do calculations to determine equilibrium pressures and things of that nature, this is the unit that you typically should be using, typically in equilibrium problems, which is atmospheres. So a reminder, right, 1 ATM is 760 torr, and that's 760 millimeters of mercury, right? Now, later on, when we do some calculations involving pressures, and maybe we have just initial pressures and we want to figure out what everybody's equilibrium pressures are, you definitely want to do the calculation in atmospheres. And that's even if, which is a very common problem you sometimes come across, even if they give you the pressures in like torr and they want you to give the answer in torr, much like when you use something like the ideal gas law, you got to put everybody in the right sort of units to put it in there. You should have them in atmospheres when you do the actual equilibrium calculation and then convert it to whatever units at the end of the calculation. So just keep that in mind. That does sort of happen along the way here. So obviously here we would use a Kc expression for anything that involves concentrations. We have pressures, which obviously would indicate that you should have gases. You could write a Kp expression for it, also an equilibrium constant. The value of Kc and Kp are usually not the same numerical value, although there are situations where they can be the actual same number, but in most cases they are not going to be the exact same number, but they do tell you the same thing. So one thing that you should learn really quickly is if you see a K, an equilibrium constant, it really does not matter what the little letter is underneath it. They are all the same thing. They're all equilibrium constants. They're all equilibrium expressions, and they're all calculated the same way. You take products over reactants. So they tell us the same thing. So if you have a large value for Kp, you would mainly expect more products to be there at equilibrium. Just like if you had a large value of Kc, you would expect more products to be there at equilibrium, and vice versa. If you had a small value of Kp, you would expect more reactants to be there at equilibrium, just like if you had a small value of Kc, you would expect the same. It works the same because if I have a large value of Kc or Kp, that means I have more products. And if I have more products, most likely those gas molecules are causing a lot more collisions and causing a lot more pressure, which is going to in turn give me that bigger value for Kp than I would if I had a small value of, say, Kc. I would have less gas molecules on the product side and a lower Kp value because there wouldn't be as much pressure, right? So you're basically doing the same calculation here with concentrations or pressure. Pressure is usually happens when you have a lot of gas molecules banging into things, right? So if you have a lot of gas molecules on the product side, you're going to have a lot more pressures, higher Kp, lower gas molecules on product side, less collisions, lower pressures on the product side, lower value of Kp. Now, there is a way that you can go from Kp to Kc, and that is this formula right here, which is the Kp value is equal to the Kc value times RT delta N. These are our favorite things from our ideal gas situation law. The R is the same gas constant you would use in the ideal gas law, which is 0.08206. Although a lot of people now round to 0.0821, whichever number you like. Liters, atmosphere, Kelvin, mole, although the units aren't super important right now for us. T here is probably like anything else involving gases, right? It's going to be in Kelvin, right? So you got to make sure that guy is in Kelvin. Now, probably the most important situation in this formula is right there, and that's the delta N. And the delta N is the number of moles of gases on the product side minus the reactant side. And that gives you your delta N. Why is that the most important thing? Well, let's just say I had this situation here where I had 2A, that's a gas, goes to B, that's a gas in this case. My delta N in this case would be, how do I know how many moles I have? I look at the coefficient, right? Of anything with a G in front of it or behind it, I guess. So on the product side, I have one gas molecule, right? And on the reactant side, I got two gas molecules. My delta N is -1, yes? It is not just the difference, which is a common error that people make. And they just go, wow, the difference is 1, right? The negative is quite important here because if you just think about it mathematically and you take RT to the 1 versus RT to the -1, is that different math? That is, right? The one on the right there, you got to take 1 over it, right? And the other one, you don't do anything basically with it, right? So very common error that people do make is when they're trying to figure out the moles of the gas, they just kind of take the difference and they sort of ignore if it's positive or negative. So you don't want to do that because again, if it's negative, you are going to be doing some different sort of math as you do it here. Now you may be asking yourself, why would you maybe need to convert between Kp and Kc? The reason is simply, for example, maybe you have all concentrations given to you and you're interested in maybe the Kp value, right? So you could use those concentrations to calculate the Kc and then use this formula to calculate the Kp and you would have it. Or maybe pressures and you need to know something about concentrations and you need to get to Kc. So this is a way that you can kind of go back and forth from it. By the way, when we do put anything into these equilibrium expressions, they do have to be equilibrium concentrations to go into these expressions to get an actual value, or they have to be equilibrium pressures if you're going into the Kp. They cannot be initial concentrations or initial pressures. They do have to be equilibrium to go into these expressions that we see here to actually get values, right? So you got to make sure that they are. Any questions on that there? All right. So in a homogeneous equilibrium here, we got a little acetic acid dissociated into acetate and some hydronium ion, and we can write our equilibrium expression like normal. Now, there are a couple of things that happen when we look at the equilibrium expression or we write the equilibrium expression. And one of those things are there are certain things that really do not affect equilibrium. And one of those things that don't affect equilibrium are things that are pure liquids. And that is because their concentrations are usually fairly large, like water, that it really kind of remains constant throughout the situation here. So when we look at it, because water remains constant, we actually do not include it in the expression because of it being a constant sort of value. And we end up really with the equilibrium expression for this reaction. If we were going to write it, this would be the proper equilibrium expression here for our reaction, which is our products, which is the acetate times the H3O plus divided by the acetic acid. Once again, we would leave water out of the expression as it doesn't really change. I'm going to just kind of preview and talk about the other thing that really doesn't change, and we'll see it in just a bit, but it is actually things that are solids. So the two things that you typically do not include in the equilibrium expression is anything that's a solid or a liquid. Solid for the sort of opposite reason, if you want to think about it. If solid, you can think of it just like it's sitting there, not doing very much, right? So if you think about the only way it could kind of participate is it's got to maybe start to dissolve and it's no longer a solid or something like that. So solids and liquids are not included. That really does just leave you two things that are included. And what is included are things that are in the aqueous state or the gas state. So those two things always go into the equilibrium expression. Things that are solid and liquid are basically left out in this case because, again, they're not really participating. They don't really change all that much over the whole sort of process. And as I mentioned earlier, equilibrium constant is typically just a number. Very few people ever use units with it. I've only seen one person ever. And that's really because, truthfully, they don't cancel out nice and pretty in this situation. So you can end up with some weird looking units. So typically speaking, we do not include the units with the equilibrium constant because of that. Any questions on that? All right, so take a moment here for each of these, write the Kp and the Kc expression, if possible, to write both. For each of these reactions, these are both reversible reactions here. To write the Kc and Kp if possible for these guys. Over reactants. So we'll start with the first one here. We'll do our Kc, and that would be the concentration of NO2. Once again, there is a 4 here, so we do need to take it to the 4th power. We're going to times it by our other product there, which is our O2. That will be divided by our reactant, which is the concentration of N2O5. Once again, it does have a coefficient of 2, so we do need to square it in that case. Yeah. Any questions on that there? For this one, we can write a Kp because we definitely got gases going on there. So our Kp in this case expression would be pretty much the same, except this is going to be partial pressures. So it would be the partial pressure of NO2, and we would still take it to the 4th power times the partial pressure of O2 divided by the partial pressure of N2O5 squared, basically. So basically the same deal, just with pressures in that particular case. Any questions on that one? Yeah. Every equilibrium constant expression is always products over reactants. So in this situation up on top, the difference between these two is if you were going to calculate the Kc, you would need the equilibrium concentrations of everybody, their molarities. For the one on the bottom, you would need the equilibrium pressures, like their atmospheres for everybody at equilibrium. And that would give you the two different values. Yeah. Other questions? Looking at the bottom one, we're going to go with our Kc here, which again is our products, H3O plus, our F minus. Everybody has a coefficient of 1 in that case. our HF, and should I put the water in? I should not. Again, this will not be included because it's a liquid. And again, if you do have a solid, as we'll see shortly, you wouldn't include that as well. So that would be it. Can I write a KP for the one on the bottom? I cannot. There's no gases, right? So you need some type of gas there to have a pressure. Without a pressure, you can't write a KP. Do you have a question? Back me. Correct. So this let me so it's a very good question actually, and it's a question sometimes people don't ask, and sometimes when they go to answer the question, answer it wrong. So just so we're clear, when you're asked to write the expression, either the KC or the KP expression, this is what we're looking for. Yeah, okay. When you want to use that formula that we just saw on the previous page, that would be a calculation-based type of thing where either you have the KC or you have enough to get the KC, you want to calculate an actual number for the KP, or vice versa. You have enough to calculate an actual number for the KP and you want to get like the KC or something like that. So you should think of that last one as sort of like a calculation type of thing. Anything that says expression or write like the KP expression or KC expression. It should simply just be based off of the reaction, the equation, and taking the products of the reactants. Yeah. Yep. Other questions? All right. So why don't we try one with the calculation here and see how we do? There we go. The equilibrium concentrations of the reaction between carbon monoxide and molecular chlorine to form CoCl2 at 74 degrees Celsius. So we got the concentration of CO is 0.012, 0.054 for Cl2, and CoCl2 is 0.14. We want to calculate both the Kc value and the Kp value. Give it a go. See how you do. Should we take a look? All right, we were looking for both the Kc value and the Kp value. If I was thinking about it logically, which one would be a good one to start with? Yeah, it would be the Kc. Obviously, here we are given concentrations. These are equilibrium concentrations. So really to do the Kc, all we have to do is just write the expression and then basically stick the numbers in. So we'll start with the expression. So this is our Kc expression, which again is going to be our products over our reactants. So it's going to be the concentration of CoCl2 divided by Co and Cl2. And since we were given all that information, we're just going to pop the numbers in there. We got a little 0.14 action, right? 0.012 and a 0.054 there, I think. And if you do all that on your calculator, you get something like a 216. I don't know if you still care about sig figs at this point. Maybe a 220 on the sig figs, whatever way you're going with that. But you do get something like that along the way as our Kc value. Yeah. Question. It's all up there. So now that we have the Kc value and we want also the Kp value, we can now use that formula that we saw earlier to allow us to really convert between them. Because really with the piece of information given to us in this problem, we have really no direct way to get to Kp, right? So we're kind of using the equilibrium to get to Kc, and now we can relate it to what our Kp value will mean in this case. So there are a few things we got to figure out. First off, obviously R is a constant, so you got your 0.08206. You got a temperature that does need to be converted into Kelvin. So our temperature here is 74 plus a 273 in that case. And that's going to get us here, like a 347 Kelvin. So we got that. We also want to figure out our delta N, right? Which is our change in our moles of our gas molecules only. So delta N in this case would be the moles of our products, gas molecules minus the moles of our reactants. And doing that, looking at the coefficient here, that's a 1 for our product side. That's a gas molecule which has a 1 coefficient, and that is also a gas molecule that has a 1 for its coefficient. That's 1 plus 1 is 2. So in this case, we do end up with a -1. In this case, by taking, again, products minus reactants. I think that's everything, perhaps, right? So we should have now everything happening over here. So going into our KP, we'll take whichever number you like. We'll go with the rounded 220 number. We're going to have our 0.08206. We're going to times that by our temperature, 347, and we're going to take that to the -1. I would recommend getting a number here, take it to the -1, and then multiply at the end. Yes, so we're going to go 0.08206 times 347. We're going to take it to the -1, which is 1 divided by it, basically. And if you do that, whoa, come here, you will end up with basically 220 times 0.035118747. No rounding happening at that point. 220. That's going to yield you a 7.7 as your KP value in this case. Again, if you took the 216, you get something pretty close, 7.6, I think. Yeah, so it's fairly close in that particular case. First off, any questions on those calculations? Yes. Say again. There's no units associated with any K value. So KC, KP, it's just a number basically. And it's really, as I mentioned earlier, it's because the units don't really cancel out really nicely in some cases, depending on what you're dividing. So what they've done just kind of keep it pretty simple and straightforward. Is pretty much everybody doesn't use any sort of units associated with it. Like I said, in all my years, I think I've only seen one person kind of use units with it. So very few, if any, will use units associated with it. Not that it's technically wrong or anything like that. There are units associated with it, but because they don't really cancel out nice and cleanly, people don't tend to use them. So here we will just use it with numbers and stuff like that. First off, large or small value K for these? Large. And they both agree with each other, right? 220 and 7.7 are both above 1. They both would be considered large. And that would mean when we reach equilibrium, we should have reactants or products here. Products, yeah. So we should expect products to be here. And again, we could kind of see that a little bit with the concentration. We actually have a more concentration of our product there, right, than we did obviously our reactants in this particular case. Any questions on that there? Before we go too far, I did want to mention something about writing the expression just to reiterate. Now, you could come across an equation when you have to write an expression where maybe you have something, I don't know, like this. And in this particular case, if we were going to write our expression, obviously we would not include this because it's a solid, right? So in this case, we would go 1 over our reactants in this particular case. Just like if you had a reaction where maybe it was something like this. Here, if we were going to write the expression, it would just be our products in this case, since we would have no reactants. So you sometimes can get a little bit of a situation where maybe one side or the other may not be included in the expression, and that's okay. And again, if it happens to be the product side, you take 1 over the reactants. And if it's just the products that are included, then you don't do anything. Obviously, no dividing by anything. It's basically divided by 1. Yeah. I would say in most cases you will have something to write the equilibrium constant expression for if that's what you're asking. I don't think you'll have come across too many where everything wouldn't be included. So there would definitely be something, but it may be a situation like this where maybe there's everything on one side you just wouldn't include, and so you have to kind of adjust your equilibrium. Other questions on that? All right, so let's take a look at another one here. I think there you go. What is the equilibrium constant Kp for this reaction at 150 is 158 at 1,000 Kelvin? What is the equilibrium pressure if O2 if the partial pressure of we'll go with NO2 on that one since they both say NO is 0.4 and the partial pressure of NO is 0.27. So I don't know if on your notes it has the T there or not, but we'll go with the 2 on that one there. Yeah. So that's NO2 there. All right, so we're looking for, in this case, what is the equilibrium pressure of O2 given this information? Okay, let's take a look. So once again here, obviously we're given a Kp actual value, and we do have some pressures given to us, and we're also looking for a pressure. So obviously Kp expression is probably where you should begin with. So if we write our Kp expression for this, again, it's going to be products over reactants. Again, instead of concentration here, we're doing partial pressures. We do need to square the NO because, again, of the coefficient times the partial pressure of O2. That takes care of all of our products. We're then going to divide it by the partial pressure squared, once again, because of the coefficient of the NO2. This actually equals 158, it says here. At this point, we have the other sort of equilibrium partial pressures, so we can put those in. And if we do that, we will end up with, we got 0.270 squared. Partial pressure of O2 is what we're looking for, divided by 0.4 squared as well, again equals 158. So mathematically, right, we're going to basically multiply that to the other side. And then when we're done with that, we're going to come back and divide that guy over to the other side, right? So if we do that, we'll get 158 times 0.4 squared. And that will essentially give us, just to break it down step by step here, we'll end up with something like this, 2528. Once again, we're going to divide that to the other side, divided by 0.27 squared. Going to yield us maybe a partial pressure for O2 about 347 atmospheres in this case. You do need some units here because this is not an equilibrium value. This is actually a pressure value, right? So the units would be obviously the same units that are associated with the others. Question on that calculation there. Again, you want to always kind of think about those things sort of make sense. So when we see an equilibrium constant of 158, is that small or large? Which means when we reach equilibrium, we should mainly have reactants or products. Products, right? If we have a large value, right? And that means that we should have a lot of products. And that means if we're looking at pressure, probably our products are contributing most of the pressure. And I would say with O2, making that big of a pressure is definitely contributed most of the pressure, right? So again, these things should sort of make sense where you kind of look at your answers and stuff like that. Any question? Yeah, so again, as I mentioned earlier, units aren't going to work out really well because technically speaking, the 158 has units associated with it, even though we don't write it. So that's how you get back to atmosphere. So the short answer is if you're solving for something like a concentration or if you're solving for something like a pressure in these type of situations, the pressure unit should probably be atmospheres, which is what the other ones were probably in, and the concentration would probably be molarity. So remember, right, even though we don't, and most people don't include the units here, technically speaking, the units are there, and it would be the units that you get here, and that's how you would get back to really those same atmosphere units at the end. So the simple way is just, put it the same units as everybody else, basically, and you'll be in good shape. Yeah, unless you have other questions. So we sort of talked about this and kind of jumped earlier, but as I mentioned before, in a heterogeneous equilibrium, basically what that means is everybody's in different phases. So you can see here we have some solids and we have some gases. And in this particular case, if we wrote the equilibrium expression like normal, we would take our products over reactants. But much like our pure liquids, our solids really are not going to be doing very much and not going to participate and are going to remain relatively constant. So we would not, again, include those in there. So as I mentioned earlier, this would be the proper equilibrium expression for this one, excluding obviously the two solids that are there, one on each side. And if we had to do a Kp, which we could because there is a gas molecule there, the CO2, we would write the Kp is equal to the partial pressure of CO2, and that would be it. So in general, as I mentioned earlier, what we do not include in these expressions, solids and liquids, what we do include is anything with aqueous next to it or gases. Those guys go into the expression. And again, the idea here is, if you have a solid sitting there, it's basically just sitting there, right? It's not going to participate. As I mentioned, if this was like a solution situation, the only way for this to participate is it would have to dissolve because in the solution, that's where we have our ions floating around and that's what's reacting. In a solid state, they are hooked together, right? They're not freely floating. And in that solid state, it's not going to really participate. And like I said, the only way for it to do that is to dissolve. And at that point, it's no longer a solid and it would obviously interact in the aqueous sort of state in that situation. So heterogeneous equilibrium just means we got things in different phases. Homogeneous, everybody's in the same phase. Kp, Kc, any of the Ks, all equilibrium expressions, products over reactants.